Hello, welcome back to 15-Minute Math. So today we're going to learn how to recognize f prime, f double prime graphically. So no, we're not going to be looking at the formulas. We're not looking at function rules. We're just kind of looking graphically, and it's going to be our job to decide which of these graphs are the original function, which one is the rate of change of that function, and which one of these describes the rate of change of the rate of change. Even though I've got my whiteboard pulled up, we're not going to spend much of today on the whiteboard. Mostly we're just going to be on Desmos looking at some graphs and then learning about some tips and tricks and ways to recognize one from the other. So let's go ahead and get to it. So here's kind of a typical problem that you'd see that kind of fits this vein. Notice that we've got three graphs. I've just labeled them function 1, function 2, function 3. And it's our job to determine which of these are f, which of these are f prime, which of these is f double prime. And there's a few ways we can attack these problems. And I think actually I just switched over to Desmos. Now I'm thinking I want to switch back, because if I'm dealing with polynomial graphs, which these appear to be polynomial graphs, then I can use the power rule to my advantage, right? Even though I'm thinking graphically, I can still think about how we evaluate derivatives with the function rules to help me. Because let's do an example. Let's say I had some polynomial here. And let me just come up with an example for us. So maybe f of x is x to the fourth minus 5x cubed plus 12x minus 7. There we go. If I wanted to take the derivative, f prime, well, I would just use the power rule, right? And so that would be 4x cubed minus 15x squared plus 12x. No, I'm sorry, plus 12. Right, the x drops off because that's x to the first and da-da-da-da. Okay, and if I want to take the derivative of that function, if I want to do f double prime, well, I'll just do the derivative again. It's just more power rule. 12x squared minus 30x, 12 drops off. So notice that the quartic function turns into a cubic, turns into quadratic. And so you kind of end up with, if you know the general shape of a quartic, kind of one of these doodads, and then the general shape of a cubic, and then the general shape of a quadratic, you can kind of just be on the lookout, because every time you take a derivative, the degree is going to drop by 1. So you could just go off of that and say, okay, f has got to be the highest degree, and then f prime is going to be the next highest degree, and then f double prime is going to be the next highest degree. And even if the degrees are hard to establish, you can at least look at end behavior, because f and f double prime is going to have the same end behavior, right? Either both, even end behavior or odd end behavior, because of that oscillating even, odd, even. Or if we started with an odd, it'd be odd, even, odd, right? So the end behavior is going to be the same. So you can use that to determine, your f prime, f double prime, even though we're thinking graphically. You can think back to consequences of the power rule, and let's do that. So if I'm looking at these three graphs, it's looking to me like this red graph, function 1, it seems like, is the quartic. What is this? Function 3 is looks like cubic to me, and then function 2 looks like quadratic. So if it was me labeling these, and there we go, I would say that right there is f. Function 3, which was the blue one, is f prime, and then function 2 is actually f double prime, based off of what we just said. Now let's look at some other ways, maybe more, because who knows, maybe these aren't polynomials, and so if we don't have a polynomial graph, we can't just rely on that. Let's look at some other ways. Now, let's just recall the red graph we're assuming is f, and then the blue graph we're assuming is f prime, and then the quadratic here is f double prime. So how could we tell if it wasn't for that? Well, here's what I would think. I would go across, and you could just test these functions one at a time, but since I already know or at least have a suspicion of what the correct answer is, I'm going to go off my red graph here. So if I'm looking at the red graph, I just pick out points where I could think about some tangent lines. So like maybe right here, if I had to draw in a tangent line, that would be the slope of that tangent line would be very steep and negative. That wasn't a very good tangent. You get the picture though. So I'm looking for which of these graphs at this corresponding point here is the function value should be a big negative number. And so I'm just kind of looking, and if I go along this dotted line, notice the green function would be a big positive number. Well, that can't be true because clearly the slope of my tangent line is negative. However, if I find the blue function, even though it's going off the screen, you can imagine if I continue this black dotted line, I would find that blue function way down in the negative somewhere. So already I'm thinking to myself, the blue function is probably the derivative of the red function. But we can pick another point, and the point I really like to look at probably is the easiest is points where the derivative should be 0. Like, let's look at the red function. Right here the derivative appears to be 0, right? I'd have a horizontal tangent. Here the derivative appears to be 0. I would have a horizontal tangent. Same deal here. So now I need to look, which of my functions have zeros at those corresponding points in the blue function, right? If I go down, the blue function has a 0, blue function has a 0, blue function has a 0. So again, more evidence that the blue function is probably the derivative of the red function. And so to me right away, at this point I would be convinced, and you could keep picking points and saying, okay, well, what about here? Let's draw in a tangent line. Which function has a function value that is, I don't know, not super steep, so kind of small and positive? Well, corresponding point. The tangent line for, I'm sorry, I almost misspoke. We don't want to think about tangent lines for these functions. We want to think about function values. The function value here is positive. The function value here is negative. And so blue, again, the blue function is the one that works, because remember what we're looking for. The function value should be the value of the slope of the tangent line, and the slope of the tangent line here is kind of a smallish positive number, and so this has a function value that is a smallish positive number. And so that graphically, that's ways that you can identify. You can just pick points, think about a tangent line, and then say, okay, which of the other graphs have function values that match up with the corresponding tangent line, or the slope of the corresponding tangent line, I should say. And you can always test points where the derivative is 0. To me, those are the easiest points to pick out because I'm just looking for the zeros of the corresponding function. So let's go ahead and let's see if those same tactics worked to prove that the green function is the derivative of the blue function. Okay, so again, where would this tangent, or where would we have horizontal tangents, which is to say, where is the derivative going to be 0? About there and there, I would say. Now, does the green function have zeros at about those points? Sure enough, there we go. And so it's looking like to me that the green function, it's at least conceivable that it is the derivative of the blue function. Again, if you're not convinced, you could just pick some points, like maybe here, draw on your tangent line. Think about the value of the slope. So the value of the slope is sort of steepish, but definitely positive. And so let's kind of draw in a little dotted line so I can see corresponding function values. Notice when I'm trying to make a determination, I'm thinking about the function values that match up with the slope of my tangent line. And remember, I don't know exactly what the tangent line slope is, but it's definitely positive and it's not huge. And so to me, the green function value kind of matches up with that, because the red function value is basically 0. So if I wasn't already convinced that the green function was the way to go, this would be further evidence. And then you could just keep, doing your tangent lines and then trying to justify to yourself that the green function is in fact the derivative. So one more time, function 1, which was the red function, that's definitely our original. Function 3 was the blue function, so that would be our f prime, and then function 2 would be f double prime. All right, I'm going to pause this video and I'm going to reconfigure the screen so that we have 3 more functions to look at, and we'll see if we can decide which one is the derivative of which. All right, so here's our new set of functions. And again, I don't know which one's which. I've just labeled them functions 1, 2, and 3. These seem to be periodic, kinda. The amplitudes are changing, but they don't necessarily seem to be polynomials. They seem more like sinusoidal sort of things. So our old power rule thing isn't going to work. And so what we need to rely on now is probably just those tangent lines and see if we can decipher, which one is which. So, well, last time the red function was the original, and then we kind of went from there. So maybe we should just assume, let's just assume the red function is f, and let's see which one would be f prime if that's the case. So let's mark off where our horizontal tangents would be. So our derivative would be 0 here. We would have a derivative of 0 here, derivative of 0 here, derivative of 0 here, right on those peaks and valleys. Remember, peaks and valleys are going to be where our derivative is 0, which is to say it has a horizontal tangent. And now which of these functions has zeros right at those points? None of them, right? So if I draw in, I'm looking for a function value of 0. Well, none of the functions have a function value of 0 there. None of the functions have a function value of 0 there. They both have it here. That might just be coincidence, because it also doesn't work here, and it doesn't work here, which tells me that my assumption was probably wrong. I would say this red function has to be f double prime because it's not the derivative of any of the other two functions. So red is f double prime. We're just going to have to keep that in mind because I'm pretty sure if I erase one thing, I have to erase everything. So let's just keep in mind red is f double prime. So let's make a new conjecture. And I honestly don't even know. I kind of forget which one is which. So let's just say, let's do the green function. Maybe green function was the original. And so let's erase. And let's do the same thing. Let's mark off where the horizontal tangents would be. About there. Maybe about there. Right there. Right there. Right there. Oh my gosh, I missed. Make my dot bigger. There we go. And right there. All right. So we know the red function is f double prime, or at least that's what makes sense right now. So that leaves the blue function. So the question is the blue function the derivative of the green function? And let's see. If the blue function is the derivative, we should see the blue function having zeros at these horizontal tangents. And even though I can't really line my points up very good, it seems conceivable that this 0 probably lines up there. This 0 lines up here. These zeros are on top of each other. Hey, it looks like oh no. I'm not sure what's happening. I'm not sure why I've got super zoomed in all of a sudden. Let me fix this, hopefully. No. Let's just erase. Let's undo. Okay. That was interesting. Either way, hopefully you got the picture. Every time that we found a horizontal tangent on the green function, that corresponded to a 0 of the blue function. So notice horizontal tangent would be about there. We have a 0. Horizontal tangent would be about there. We have a 0. Which tells me that the blue function is probably the derivative of the green function. So we found it because we already know that this one was f double prime. So that means the blue function is f prime, which means that the green function is f. Okay, and so let's see here. Green was function 2, red was function 1, and so now we can go ahead and label them. So function 2 was f, this was f double prime, and this was f prime. So finding those horizontal tangents can go a long way. Just remember they are going to correspond to zeros of the derivative, and you can kind of just play that game. If you need to go further, you can always just kind of estimate tangent lines and see corresponding function values. And remember that if you happen to be looking at polynomials, you can use that power rule to your advantage as well.